So, what kind of functions allow you to do improper integrals? What, is this an improper integral of what kind? This is the first kind, isn't it?
First one, right?
Yeah. First kind means the limits of integration, one or more of the limits of integration are infinite. Second kind means there's a singularity in the integrand. And third kind means you have both defects present. So you have to worry a little bit about the convergence of the integral. If f of t is a really fast-growing function, it might be that e to the minus st f of t doesn't go to 0 as t goes to infinity, which is going to happen for this integral to converge, right? The whole idea is no matter what f of t is, this is the hammer. E to the minus st, as t gets larger and larger, e to the minus st gets smaller and smaller, and kills anything that lies very, very far away from the t origin, right? If you have a pathological function, it doesn't really have to be too pathological. If you have a function that defeats the ability of that e to the minus st to hammer it, so that it doesn't go to 0 as you go to infinity, what happens to the integral? You know, if you integrate the function from 0 to infinity, epsilon dt, where epsilon is definitely greater than 0, what do you get? Right? It doesn't converge. There's a little lump there. You know, it's the mouse and the snake. You can't get rid of it. Maybe that's not a very tasteful metaphor, but anyway, that's how it goes. It's got to go to 0 as you go to infinity. So another thing about Riemann integrals of this type, improper Riemann integrals, you would like this. You can't hope for continuity all the time. Continuity is a lot to ask for, but sectional continuity or piecewise continuity is good enough, right? Because you can always start and stop the integral to accommodate a finite number of discontinuities. That's easy enough to do. A countably infinite number of discontinuities, that's a little trickier. What we would like to insist on is that f of t be two things. Sectionally continuous, that means it's only discontinuous at a finite number of points, so that we can stop and start this integral whenever we have a bump in the road there. We stop the integral and start it up again. So we drive only on the continuous intervals, okay? Stopping and starting whenever we need to, and we can only tolerate a finite number of points. And the other thing is that f of t has to be of what they call exponential order. And you say f of t is exponential order, gamma, whenever this is true. Whenever this is true, the limit as t goes to infinity of the absolute value of e to the minus gamma t f of t is 0. There, this is the integrand. This is the integrand being pushed to 0 for very, very large t. You have to be able to find a gamma that's making this true. Alternatively, you can rephrase this. You can rephrase this so that e to the minus gamma t f of t is less than a fixed constant m for some gamma way out there. And then, of course, as t gets larger and larger, it gets smaller and smaller. But the point is, it's bounded by m. So another way to view this is f of t cannot grow exponentially, because if it grows exponentially, it can defeat this discounting factor or deflation factor, right? This is a reduction factor. If this thing is growing so strongly that it defeats this one, it's going to grow bigger than any constant, and the limit certainly isn't going to be 0, right? You can't tolerate that. So what's a function that has exponential order and what's one that doesn't? E to the
e to the t is exponential order.
e to the t. So if we had e to the minus gamma t times e to the t, what would that be? E to the t times 1 minus gamma, right? As t goes to infinity, as long as gamma is greater than 1, right, this exponent would be net negative, and this thing would eventually go to 0. So e to the t is okay. How about this one? What if you had e to the t squared?
Yeah.
And if you multiply that by e to the minus gamma t, of course you get e to the t squared minus gamma t, which is e to the t times t minus gamma. Well, for fixed gamma, eventually, this is going to be positive as t gets bigger and bigger. And then this thing is going to...
On screen, please.
Huh? Oh, I'm sorry. You have to tell me that. I don't know. I just...
You didn't understand what this meant?
Ever so... You know, I shouldn't do this, but I'm going to do it anyway.
Draw a line.
Okay. You do.
Wipe it off.
Okay. So this one is not an exponential. So the Laplace transform of that would be existing. This thing's blowing up as t goes to infinity. So those are our two demands: sectionally continuous and of some exponential order. So that e to the minus stf does go to 0. That's a good integrand, sure. Okay. Now we're in a position to just grind through the definition. Maybe that's the wrong word. I want to encourage you. Since we're, yeah, grind, but I know.
Easily found.
Easily found. Inspirationally determined. So Laplace transform. So
Make
what's
perfectly clear. That's the way we do it.
if f of t is the one function, what is the Laplace transform? Okay. Well, then f of s would be the integral from 0 to infinity, e to the minus st times 1, right, dt. And that would, okay, calc 1, e to the minus st.
Did you scratch the pen again?
No, I think this,
Just kidding. I'll take it almost that was minus those two.
I give him a client that pen is just going to start writing small.
I got about 3 dozen of them. I asked Kathy to get me a bazillion of them. And I start the day, and they look very nice. And I must get mad or, I don't know, leaning on them.
You're great.
They look like those magic markers by the end of the day.
You're very unique. You wrote your own that.
What's that?
You have a feather, you're writing with it.
Right, with a quill.
Well,
You look really smarter, much smarter.
is that a green eye shade maybe?
You have to curve all your letters and stuff.
Oh, don't get me started, because I can do that.
Oh, when we start writing letters, I don't like.
We can use the Gothic
No,
letters.
thank you, that's right.
Fell off the track. We had topology a couple of summers ago, and they didn't like my calligraphy, the Gothic A's, that sort of thing. And I say, what the hell is that?
Well,
It's
you
an
always,
H.
so it always be like, let's pick a variable. How about Gothic?
A letter.
Not like X or something.
I probably did that just to make the
You
change.
should have done that in that business conference class you took.
Then they would have hated me even more.
So what?
Yeah.
They didn't go here, most of those kids didn't go here.
Well, that's another summer class. I told you that
Yeah.
it's the bimodality there.
They were from FSU or something.
All right. Can anybody do this interview?
No rest.